Hello, everyone, and thanks so much for the opportunity to give this talk. Here, Jenny Sukala, Sonia Tiku, and I will trace the observational, experimental, and theoretical evidence for how water is delivered to growing rocky planets and how it is processed and partitioned through magma oceans and atmospheres. This framing may give us all a structure to react to in agreement and in disagreement during our upcoming conversations. First, water is added with the rocky material that creates the planet. Certainly, water is added also later through both rocky and icy impactors, but a key concept is that the rocky material that created our Earth contains sufficient water to make Earth habitable. Some people have thought that Earth was formed dry and that only later cometary impacts could account for the water on the surface. This data set, though, and others like it, show that most comets have a D to H ratio in their water ice, a deuterium to hydrogen ratio, that is too high to match Earth water. That's the horizontal axis here. You can see the comets are here, and here's Earth right here. And in fact, comets' organic molecules have a D to H that is even farther from the Earth's value. On the vertical axis here, you see that all comets so far measured have nitrogen isotopes too heavy to explain the Earth. Further, noble gas compositions on the Earth limit cometary contributions to 1% or less. Earth's water, in fact, seems to come from the same material that seems to have built the whole planet, the class of meteorites called enstatite chondrites. And in a number of the slides of this short presentation, I've added a whole bunch of references at the bottom to try to at least dip into the vast literature of the people who've studied this problem. Now, after each of the giant impacts of planetary formation, water is processed through the solidifying magma ocean and thereby partitioned between the mantle and the atmosphere. The magma ocean liquid is dominated by silicate melt, but it also contains dissolved volatiles, including water, carbon, and sulfur compounds. With the possible exception of a relatively thin basal layer, the magma ocean solidifies from the bottom upward. Water and other volatiles will be incorporated into the nominally anhydrous mantle phases up to their saturation limits. Although in most magma ocean models, they do not reach saturation in any way using sort of chondritic levels of water. And water will otherwise be enriched in the remaining evolving magma ocean liquids. The water content of the resulting cumulate mantle is therefore the sum of the traces in mineral grains and any water trapped in interstitial liquids. That trapped liquid fraction may in fact be by far the largest contributor to the cumulate water budget that's available to later degas through volcanoes and add water to the surface of the planet. The process of degassing for the magma ocean, however, remains poorly understood, and I'll show two ideas in the next slide. It's been assumed in almost all magma ocean papers that volatiles in excess of saturation continuously degas from the magma ocean. But to degas into the atmosphere, the gases must exsolve from the liquid and form bubbles, and those bubbles must be able to rise quickly enough to avoid being dragged down by convection and redissolved at higher pressures. But if bubbles are buoyant enough, that is large enough to decouple from the flow and rise, then they're also dynamically unstable and liable to be torn into smaller bubbles and then re-entrained. So this conundrum led to the hypothesis by Jenny Sukala and myself that volatiles do not significantly degas until a high level of supersaturation is reached, and the bubbles then form a buoyant layer and rise and diappears in a continuum dynamic sense. This late degassing would have the twin effects of increasing the water content in the cumulates for later degassing from the planet and of speeding up the cooling and solidification of the planet, possibly letting the steam atmosphere cool and collapse before it is stripped by the UV of the sun. Meanwhile, inside the now solid cumulate mantle, following solidification, the cumulate mantle is gravitationally unstable. That is, the densest materials lie closest to the planetary surface. This example is from Miyazaki and Kornaga 2019, but many investigators have similarly found that toward the end of solidification in particular, the mantle cumulates are denser than their underlying materials due both to thermal and compositional characteristics. So here is a result from Tiku and Elkins-Tanton 2017 investigating a possible outcome of that unstable density profile. Model results are shown for a 2,000-kilometer deep terrestrial magma ocean with an initial water content of 0.25, just 0.25 weight percent, 2,500 parts per million. The figure shows water content of the cumulative mantle on the horizontal axis right here, and the radius of Earth on the vertical axis. The upper curve, which starts down here and ends up here, this gray curve, is the relatively far higher water content of the shallow mineral assemblages really show here. These minerals are able to accommodate more water in void space. And so as the magma ocean solidified from the bottom to the top really has most of the water, but it's also the densest. Now, after it overturns to gravitational stability, calculated according to the density of the phases, the lower curve shows where that water-rich material ends up after gravitationally driven overturn. Now notice the blue dashes, this line right here. That's about the water saturation limit of minerals in the lower mantle. Driven by their high density, the originally shallow water-rich layers will have dewatered as they sank through into the transition zone. So this is what that dewatering zone would be, going through the transition zone into the lower mantle. Upon converting to lower mantle phases, these minerals will release their excess water. Since lower mantle phases have lower saturation limits, there's their saturation limit here, but this is how much water was actually in those minerals, then thus fluxing the upper mantle with water. When fluxed with excess water, the upper mantle would be expected to form perhaps a low degree melt because its temperature would be quite near to its solidus still. If it's voluminous enough, that could help kickstart plate tectonics. It could further reduce the viscosity of the asthenosphere. The releases are, say, between 10 parts per million and a few weight percent. So finally, we have a view that's something like this. On the horizontal axis is time, starting on the left with the most recent giant accretionary impact, something like our moon forming impact. On the vertical axis is the fraction of magma ocean volatiles degassed into the atmosphere. You see that the peak in loss from the planetary interior to the atmosphere occurs during magma ocean solidification. Modeled atmospheres at this stage receive between about 60% and 99% of the water and CO2 that the magma ocean began with. Then there is a small additional loss during compositionally driven overturn of that unstable density profile. And then there's a period of quiescence as thermal convection slowly overcomes compositional gravitational instability and begins again to mix the mantle, after which some level of volcanic degassing persists. And this is approximately to scale for the Earth of what the volcanic degassing of water is today compared to what it would have been during the magma ocean. Thank you so much for your time and attention as I talked about the fate of water in the formation of rocky planets.